Section 7.2 talks about definition of the Laplace transform. Definition 1 says let f of t be a function on 0 to infinity. The Laplace transform of f is the function f of s where you integrate from 0 to infinity this function f with respect to t, but you multiply it by e to the negative st. If I have time at the end, I would love to show you 7.1, and that's where they really explain what all of this is about. The domain of f of c, f of s is all the values of s for which the integral exists. The Laplace transform of f is denoted by this notation. And that's how we're going to write it, or simply s. Sometimes we write y, it's the same thing. So use definition 1 to determine the Laplace transform of the given function. And the way it works, this is on page 360. So the Laplace applied on t squared, we call that f of s. It's simply the integral from 0 to infinity of e to the negative st times t squared dt. So if I let u equal t squared, take a derivative, another and another, dv is e to the negative st. If you integrate, again, and if you integrate again, and if you recall, so this is going to be t negative t squared e to the negative st over s minus 2t e to the negative st divided by s squared minus 2e to the negative st divided by negative s cubed, and that's going to be evaluated from 0 to b, taking the limit as b approaches infinity. And that would be limit as b approaches infinity of negative t squared e to the negative s b squared minus 2b e to the negative sb divided by s squared minus 2e to the negative sb divided by s cubed minus, if you put the 0 in, you get a 0 minus 2 over negative s cubed. And that turns out to be, this would be 0, this would be 0, and this would be 0 if negative s is positive, or s is negative. This will approach 0 too because exponentials dominate over anything. And if you distribute that in, so that is 2 divided by s cubed. So anything with an exponential will converge if the power stays negative. And if I want to apply the Laplace transform on t e to the 3t, the same deal, that's f of s. That's the interval from 0 to infinity of t e to the 3t times e to the negative st dt. That would be the integral of t e to the 3 minus st dt. infinity, the same deal, we let u equal t, du is 1 and a 0, dv be e to the 3 minus s t, so that's e to the 1 to the 3 minus s t divided by 3 minus s, and that will be e to the 3 minus s t divided by 3 minus s squared. This would be negative because of the minus, and negative times a negative is a positive, so this is a positive and a negative. That would simply be the limit as b approaches infinity of negative t e to the 3 minus s t over 3 minus s minus e to the 3 minus s t divided by 3 minus s squared, evaluated from 0 to b. That's the limit as b approaches infinity of negative b e to the 3 minus s b divided by 3 minus s minus, let me shrink that a bit and shove it aside, e to the 3 minus s b divided by 3 minus s squared minus, if you put a 0 in, you'll get a 0, minus e to the 0, which is 1 over 3 minus s squared. Now, this will approach 0 and this will approach 0 as long as 3 minus s is negative, which means as long as s is bigger than 3, that will approach 0, and you're left with 1 over 3 minus s squared, or simply 1 over s minus 3 squared, because those two are doing the same exact thing. Now, if I look at a function, and here of course s has to be bigger than 3, it's right there. If I look at a function, a piecewise function, well, if I want to find f of s, that would be the Laplace applied on f of t. That will be the integral from 0 to infinity of f of t e to the negative st dt. That is the limit from 0 to 1 of 1 minus t e to the negative st dt, plus the integral from 1 to infinity of 0 times e to the negative st dt. Well, that's 0. So I am left with, take a derivative, another derivative, dv is e to the negative st, e to the negative st divided by negative s, e to the negative st divided by s squared, plus minus. So that is 1 minus t e to the negative st over negative s. Negative times a negative is a positive, e to the negative st divided by s squared, evaluated from 0 to 1. And if you put 1 in, you'll get a 0 plus e to the negative s divided by s squared minus, put a 0 in for t, that will be a 0, that will be 1, so that will be e to the negative st divided by negative s plus 1 over s squared. So the answer will be e to the negative s over s squared plus I forget to put the 0 there, plus 1 over s minus 1 over s squared. Now, Laplace transform, the power of that, if you apply the Laplace transform, we can figure that out by using the following table, which you could use on your test. You can print this out and have it ready, and when the time comes you could use the test. Here's the catch. Every time you use the table you have to tell me what number you used. So if you print this and put it right next to you, if you apply the linear plus transform on the sum of two functions, then that's the linear of the sum of the linear of the functions. And if there's a constant involved, you can drag that up front. That's not an issue. So using this table, if I want to use the Laplace applied on 5, well, I look for 5. I notice 5 is number 1. That's a constant. The Laplace is going to run as 1 over s in this case. So 5 times 1 over s. And you have to tell me by which number. That was by property 1. Minus e to the 2t. E to the at, that's 4. It's 1 over s minus a. It's 1 over s minus a, and this is by 4. And this is 6t squared. If I move up to t squared, t to the n is n factorial over s plus 1. So it's going to be 2 factorial divided by s to the 2 plus 1, which is 3. And this is by property 3. So every time you use the table, you have to tell me whether you're moving forward or backward. How are you doing this? Here again, according to the rule up here, right, the L applied on multiple functions, that would be L applied on t squared minus 3 the Laplace applied on t minus 2 the Laplace applied on negative e to the t sine of 3t. And if I do apply the Laplace by 3 t to the n factorial over s, so n factorial over s to the 1 more than the 2, which is 3, minus 3 applied on t. Oh, but I forgot to mention this is by 3. And if I apply the Laplace and transform, okay, that's 1 over s, that's by 1. And the Laplace applied on e to the negative s sine of t, sine of 3t. E to the negative t, it's right there. The sine, that will be, so here's how it works. E to the at will shift s, the original s, by s minus a units. Here, e to the at shifts this by s minus a, but those are the same. This is the square of that and a plus. And if I'm looking at sine, that's 7. So that is 3 factorial divided by s plus 1 squared plus 3 squared. That is by 7. And if I apply the same rule, if I apply the Laplace, that's really f of s on t to the 4th, that is gonna be 4 factorial over s to the 1 plus 4, which is 5, minus, this is 2 factorial, which is 2 over s to the third, minus, if it's a t, 1 over s squared, plus, and according to the table, if you're applying that Laplace and sign, that's a over s plus a squared. That is a over s squared plus a squared, which is a 2. And that will be my answer. Laplace applied on the cosine. Well, this one is going to be, let's see, you're shifted by s plus 2. That's going to be s plus 2 over s plus 2 squared plus, what do you square to get that? Well, that's a 3, and that is by 8, minus 2 factorial over s plus 2, and that will be cubed. Alright, what else is there? This is by 3, this is by 2, and this is by 5. This was by 9. Now the last piece of this section, we talk about continuity. Definition. A function f of t is said to be piecewise continuous on a finite interval if f is continuous at every point except at possibly some finite numbers at which you have just a jump discontinuity. A function f of t is said to be piecewise continuous on 0 to infinity if after some n it is continuous or certain interval. Determine whether f of t is continuous, piecewise continuous, or neither continuous. Sketch a graph. A rough sketch. Zero to 2. And 2, 2, with a slope of 1 all the way to 10. So that's what the graph looks like, something like that. Of course, I could rescale this if I want. If I take the limit st approaches 2 of f of t, that's the limit st approaches 2 from the left, and limit of a constant is the constant, the limit st approaches 2 from the right, and that is 2. Well, since the limit does not exist, we know that there is a jump discontinuity. F has a jump discontinuity at t equals specifically 2. Therefore, f is piecewise continuous at 0 to 10 . This is t minus 2 into t minus 1 over t minus 2 into t plus 2. These cancel out. So if I look at the graph of this, vertical asymptote at x equal negative 2, horizontal asymptote y equal 1. If x equals 0, I get negative 1/2 and a 1. And if t equal 2, y would be 1 over 4. We have a hole on the graph, and we know that the limit as t approaches 2 of t minus 1 over t plus 2 equal 1/4. So f has a removable singularity at t equal 2. And it is a piecewise continuous on zero to 10. If I look at the graph of this, so if I pick a point to the left of negative 1, say negative 2, that is negative over a positive that's a negative, and say negative 1/2, that's negative over a negative, which is a positive, positive 1/2, and if I pick 2, that's what the graph looks like. So if we take the limit as t approaches 1 from the right or the left, that's actually infinity. So f has an infinite discontinuity at x equal 1, t equal 1, and it is neither continuous nor piecewise continuous at 0 time. Sine of t over t, if t doesn't equal 0, and when t equals 0 we get 1. So the limit st approaches 0 of sine of t over t equals 0. We know that from calculus, and that is f of 0. So f is continuous on negative infinity to infinity, and specifically on 0 to 10, which is what they're asking about. There's no restriction on this problem. And that's pretty much it for this section.